Hello and welcome to this presentation for ITSC 2022. This paper that I'm presenting today is Pedestrian-Aware Contextual Speed Controller for Autonomous Driving. My name is Stuart Worrell and I'm here to present on behalf of myself, Daniel Zhang and Mao Shan. We're from the University of Sydney in Australia and form part of the Australian Centre for Field Robotics. So the research aim, the question that we're trying to answer is, what is an appropriate speed for an autonomous vehicle to travel at when there's pedestrians around? And this is definitely contextually driven. You can see two pictures here. One on the left is on a road where pedestrians will generally walk on the side. And the picture on the right is a shared space where people can walk anywhere they want. And as you can sort of imagine, there's two different expected behaviours for the vehicle in these scenarios. So the question we're trying to ask is, beyond things such as determining speed for safety reasons, what other speed cues should we be looking for in determining the speed that we should select? This forms part of a larger part of research where we have a number of platforms, the small electric vehicles like the ones used in this study, a larger vehicle which is used for data collection and also towards autonomy. And we also do a lot of work with infrastructure for understanding smart intersections and similar things. And it sort of fits into three main categories. Partially is actually demonstrating autonomous vehicles. Part of it is about data collection and simulation, so digital twins of an environment. And the third part is human factors, so how people interact with these vehicles, from both inside and also from outside. And the research that I'm looking for today sort of combines a few of these. We're looking to demonstrate autonomy using data that we collect to better understand the context of a situation and apply this to a human factors question. So these decisions are made all the time by people who work in this field. Autonomous driving requires speed as a choice, and this speed selection is usually based on a few different factors. One is that there's obviously legal speed limits that are required to be maintained. And the second one is looking at obstacle avoidance. So there's going to be some modulation of your speed based on obstacles that happen to be in your environment. Speed is sometimes considered to be a high-dimensional planning problem, where you can design both for speed and for lateral and longitudinal movement. But this can be quite challenging as it's a very high-dimensional problem. But with all of these considerations, social context is largely ignored, but is very important. For this technology to be acceptable by the public, there really needs to be a speed selection which is acceptable for the people in the environment around. So this research looks to understand that better by considering data that's been collected from a naturalistic driving data set. So the methodology that we've employed is to consider this as a layered problem. The top layer is the maximum speed that is determined by law. So this is very much context specific. And then the next layer that sits under this one is one which is a context-driven layer. So understanding how an environment, what the speed profile should be given an environment and also given the context of the density of pedestrians. So those two things are sort of combined together into that context layer. And then the final layer is looking at applying an analysis of a speed limiting obstacle avoidance algorithm and being able to compare that to the way that a human would perform in a similar type of context. So the first part of this is to understand the data itself. So we use a naturalistic driving data set that was collected on our campus at the University of Sydney, which covers a wide range of different contexts. We go through areas where there's very busy roads, there's very quiet roads, and there's also shared spaces where generally vehicles are not allowed to be in that space. And so as we were driving around, we started to understand that the behaviour of the vehicle should match the context in which it's operating. So the first question is, well, how do humans drive? We analyze the data from a shared space, and this is what we can see on the graph here. So this shared space is a fairly open area where the vehicle can sort of maneuver freely. It's not restricted to any particular lanes. And you can see, though, that the way that the human operated in this area, this is a normalized histogram where each of the colors represents a different band of speed. When there's less pedestrians, the vehicle generally will go slower. So you can see that if there is less pedestrians, the vehicle will generally go faster. So a small number of pedestrians, a low pedestrian density, there's some higher speeds above 20 kilometers per hour, but the bulk is between either 15 or 20 or between 10 and 15. As the density of pedestrians increases, the average speed decreases to the point where when it's very dense, as in when there's 9 or more pedestrians within the range of the vehicle, the speed is generally much slower. So there's no high speeds, very little sort of medium speeds, and then most of the time it's driving between 5 and 10 kilometers per hour. So it's a fast walk speed. So it's interesting to see that there's this relationship that's quite clear that comes just from the data that we've collected from a human-driven vehicle. And it's interesting to compare this to the driving on other roads within the campus. So not on the main roads, but on other roads within the campus, whereby the density of the pedestrians increasing does not really have much of an impact, much of a noticeable impact on the speed profile of the vehicle. And that makes a lot of sense because this road here is really designed for cars. Pedestrians are generally restricted to walking on the footpaths, and any interactions are generally much better planned. They might cross at a pedestrian crossing, or they might look before they cross, rather than in a shared space where there's more of an expectation that they can walk wherever they want. So these two things were being really combined to make that context layer, sort of a speed profile, a speed selection based on the density of pedestrians. Then the next layer is a proximity layer. This is a vehicle that we try to operate in real time, so it has to operate fast. And to do this, we have a fairly fast detector for pedestrians that fuses the information from cameras and the LiDAR. On the top here, you can see a point cloud that we then cluster. We take the images from the camera, and we use that to then work out which of the clusters belong to a person as a mechanism for understanding where the people are in the environment. And this does a very good job at finding the spatial information of the obstacles, but also being able to distinguish between a pedestrian and other types of objects in this kind of environment. So again, this is really not so much, this paper is not so much about this process, but more that this process is being used to then analyze how different parameterizations of this speed selection compare to a human operator. So the position of the people are compared against the projected path of the vehicle. So you can see here that the vehicle is going to make decisions about moving away from the people, maybe and the way that it operates, and that this path that you can see in green here is where we estimate that the vehicle will be in the upcoming seconds. So the information about where the people are relative to this path is going to be used to modulate our speed. So this speed scaling information is fed into a reasonably simple algorithm which modulates the speed based on the distance along the road to the person, to the pedestrian, and also some function of how close they are to that path. So if they're very close to the path, we have a scaling factor that it will make the speed slow down more than if it's further away. And by actually parameterizing this and making a factor in this scaling process, this is something that we can then modify to then tune the behavior of this speed selection based on how confident we are driving near the people and how comfortable people are with the vehicle traveling at speed in close proximity. So the combination of all those three lead to this determination of the final speed. So we start with the legal limit, a contextual limit about the density of the pedestrians in the environment that it's operating, and this proximity limit, which means that we don't want to drive too fast to people that are close to the path of our car. We combine these, we take the minimum of these to determine the final speed. And an example of this applied to a trajectory that was collected. You can see there's a few parts to see here, but I'll just go through them a bit at a time. The blue line here represents the speed that the driver actually drove in this shared space. This is the shared space scenario. The bottom plot here shows the density of the pedestrians. And as you can see, higher density at some parts, lower density in other parts. And then the corresponding high and low densities changes this context-specific yellow line here. So when the density is higher, the speed is lower. Then when the density gets lower, then the speed gets to be higher. Then the third part of this, the red line, is the proximity-specific speed selection. So this is the idea of understanding where the pedestrians are relative to the location of the projected path of the vehicle, and then using that information to be able to reduce the speed depending on how close the people are to the projected path. And when you combine those together, we end up with our speed profile our maximum speed as selected by our speed controller, which is the combination of those. So you can see that it's more conservative. So this purple line, which is the combination of all of the layers put together, is generally lower than the human driver. But really, this is expected, as a human driver has a much better, much more fine-tuned understanding of the situation. And that's why we're making this comparison. So you can see the difference between this real driver and our speed selector's output is what we're then going to be comparing when we're looking in the next graph. This is also just to understand, this is a maximum speed profile. This doesn't necessarily mean that the vehicle will attempt to obtain those speeds. There are going to be other smoothing controls that go on in this. So this plot here shows how the behavior of our proximity detector, this is using the proximity scaling, so understanding how close the pedestrian is to the track of the vehicle, and how it relates to the human operator. So if it was all the same, then this would be all on 0, as in the percentage, the percentage of the time it's the same as the human driver. As the speed profile is lower, it'll be less than 0, and if the speed is estimated to be faster from our speed controller, it would be above 0. So the interesting things to note from this is that we've applied different scaling factors. With a lower scaling factor, it is going to be more conservative, and this can be seen by the fact that there's more blue area, less than 0, for the proximity scaling factor. And when there's a bigger number, there's sometimes when the maximum speed is considered to be able to be much higher than the human drove. So this is more about understanding how the relationship is between this parameter that we've selected as part of our speed scaling process and how it affects the ability for it to control similar to a human driver. So we combine all of the layers together and we end up with this plot here, the one at the bottom. And you can sort of see that when you put all of the layers, including the pedestrian density context, in general, the speed selected by the vehicle is in general slower than the human operator, which again is sort of as we expect, given that the human operator is driving somewhat to the conditions, but with more knowledge about what the expectation is for the pedestrians. And similarly than before, you can see that the different scaling factors have a different weighting on this process. So really, to summarize, the contributions of this work is really one of the main contributions is to identify the fact that this needs to be something we consider when planning the speed of a vehicle. It shouldn't really just be a process of understanding the physics of a situation. If you want to have this kind of technology accepted by humans in different, accepted by pedestrians in different contexts, we need to be able to operate as people would expect. So that would be as a human driver would normally behave. We introduced a speed scaling based on a real-time detection of pedestrians, and then we developed this mechanism to be able to compare this controller, our own controller, to the human driver behavior. And the next step after this is to use this data to do some user studies to understand how people inside the vehicle feel about these behaviors as well. Great, thank you for listening.